Hello, this is Magic 063 Differentiable Manifolds. I'm Kirill Mackenzie, and this podcast is about submersions and immersions and also étale maps at the end. So here's the first definition. A smooth map is a submersion at a particular point M of the domain if the tangent map is a surjection. That's the tangent map at that point of the domain from the tangent space of the point to the tangent space of the target at the image point. And it's a submersion, without any additional words, a submersion if it is a submersion at every point of the domain. So there are lots of examples. First of all, projections from a product manifold M1 cross M2 to either factor. If we call this projection sub I, then the tangent map to the projection at a particular point, I haven't left myself much space, M1, M2, is actually the projection of the, perhaps I better write it like this, the projection of the product of the tangent spaces to whichever individual product space we chose. Okay. So here, this PR over here on the left is the projection of the product manifold to one of its factors, and this projection here is the projection from the product of the two vector spaces, the tangent space to M1 at little m1 with the tangent space to M2 at little m2 down to the tangent space of the corresponding factor. And that's certainly a surjection. The projection in a vector bundle, let's come back to that in a minute. Covering maps, in fact these are stronger than submersions. If you have a covering map, then in fact, let's just call this sort of M tilde. It's slightly dubious notation, but it'll do for the moment. Then in fact the maps induced on the tangent spaces, let's call this gamma, are in fact isomorphisms of vector spaces. So here's the local criterion. We've defined submersions in terms of an infinitesimal criterion. Here's the equivalent local one. Given a smooth map and a particular point in the domain, F is a submersion at that point. If and only if there are charts defined on neighbourhoods, first of all U in the domain containing M, and U prime in the target containing the image point F of M, such that in terms of those charts, F is a projection of Euclidean spaces. And here I've written it as R to the N prime. That's the dimension of the target space times R to the K, where the N prime plus K add up to the dimension of the domain space. Because, of course, it's clear from the definition that the dimension of the domain must be greater than or equal to the dimension of the target. If a submersion exists, then that must be true. Okay. So this is not especially hard to prove, but there is a bit of work in doing it carefully. The main thing is to know the result. And one thing that follows from it immediately is that when you do have a submersion and you do take those charts, then you get local right inverses. to the map F. This needs a bit of care. If you think about vector spaces, when you have a surjection of vector spaces, a surjective linear map of vector spaces, then there are right inverses which are linear, and there's a very wide range of them in general. Here, you cannot be certain that if I pick a pre-image of my point M prime, that there's going to be a local right inverse that goes to a specified point of M in the domain. It can happen, of course, but in general it doesn't. And this is a tricky and obscure matter. But what definitely does exist is a local right inverse. So now, consider the tangent maps. They're surjective, so they are determined by their kernels. Let's assume that we've got a surjective submersion in order to keep things a little bit tidier. Then for any point in the target, the pre-image there is a closed embedded submanifold of the domain. There's a podcast on submanifolds following this, and I'll refer you to that for this term of an embedded submanifold. Basically, that's a very good submanifold of the domain. And for all points of that pre-image, the tangent space to the pre-image is the kernel of the tangent map. And this is a global form of a result that we talked about at the start of the course, talking about zero sets, which are indeed precisely maps of this type, sets of this type. They're pre-images of points. And the kernels of the derivative matrices for these maps, with zero sets we're talking about maps between Euclidean spaces, are precisely the kernels of the linear maps. Okay, so this is a global result. Further, M itself, the domain, is the union of the various pre-images, which we normally call fibers of F. And the pre-images either coincide or they're disjoint. That's really just a little result of set theory, but it's worth emphasizing. And the union of the kernels over all points of the domain, form a vector bundle on the domain. In fact, it's a sub-bundle, of course, of the tangent bundle of the domain. I haven't talked about sub-bundles or quotient bundles, but it does follow in a fairly straightforward fashion. And this union of the kernels is a sub-bundle. It's of constant rank, and it's essentially the bundle along the fibers of this map F. It's actually an example of a foliation. I'm just going off topic for a moment. It's called a simple foliation precisely because it's defined by a submersion, and foliations in general are more complicated than that. But nonetheless, these can be reasonably complicated. They certainly don't always look globally like product decompositions. Here's the corresponding definition for an immersion. A smooth map is an immersion at a particular point of the domain if the tangent map is injective. And it's an immersion, full stop, if it's an immersion at every point of the domain. So these are direct analogues of submersion at a point and submersion on the domain. Examples: a regular curve in R2 or R3 or any Rn is an immersion. The regularity condition is that the derivative is never zero And since the domain is one-dimensional, that guarantees injectivity. And by the way, of course, in this situation, if an immersion exists, then the dimension of the domain must be less than or equal to the dimension of the target. A regular surface, likewise, in fact, we have gone through this. The cross product of the partials, never zero, that's the regularity condition, and it ensures that the derivative matrix, which has 3 rows and 2 columns, has rank 2, and that's the dimension of the domain. Product manifolds, something similar to what we saw a minute ago. This time it's the maps that inject a factor alongside a particular point of the other factor. These are immersions, and again, it's very easy to check that the tangent to this map is the vector space analog of this. And lastly, and this is perhaps a little bit interesting, a section of a vector bundle is an immersion, and that's precisely because it's right inverse to the bundle projection, and applying the tangent functor to this q comp mu equals z gives, of course, that the tangent map to mu is injective at every point. There's a local result, which I haven't written down, which is analogous to the local description of submersions, and that's somehow less frequently useful, but you can guess the result by simply looking at the result for submersions. So here's the case in which submersions and immersions coincide. It's known by the French word étale, and it's a smooth map is étale at a point of the domain if the tangent map there is actually a linear isomorphism from the tangent space of the domain to the tangent space of the target. And it's étale, full stop, if it is étale at every point of the domain. So diffeomorphisms are étale maps. That's easy to check. The converse is false, and if you think for a moment, I'm sure you know this. The simplest example is the projection from the real line to the circle. This is a covering map, of course, but the tangent space to the reals is a one-dimensional vector space. The tangent space to the circle are one-dimensional vector spaces, and this map induces the identity, or at least a linear isomorphism on them. Of course, that's not a diffeomorphism. The target is compact and the domain isn't. There's also this map here, xy in the plane goes to x squared minus y squared, comma 2xy. In other words, squaring complex numbers and deleting the origin from the plane, we get a map from the punchant plane to itself. It's certainly not a diffeomorphism, but it is étale. And more generally than that, any covering map of manifolds is an étale map. For example, the standard map from SU2 to SO3. If you aren't interested in Lie groups, you can think of this as being from the 3-sphere to projective 3 space. But in either case, it's a 2-to-1 map, covering map, and it's étale. There is a local description of étale in terms of locally the identity. Again, I won't write that down. I'm sorry, I said locally the identity. I should have said locally diffeomorphism from Rn to Rn. because, of course, if there is an étale map, then the dimensions must be equal. Étale maps are sometimes called local diffeomorphisms. I think I said something about this earlier. I'm rather against this use of the word because it's perfectly natural to use the word local diffeomorphism for something which is only locally defined on the domain and which is a diffeomorphism there. And of course, these concepts are very close, but they're not exactly the same. So I will stick with étale in the sense defined here. That's basically all to say about this at the moment. And I'll leave it there for now.